All right, let's welcome our last speaker of this session, Rouven Michels. In the ballpark?
Yeah.
Yeah. Is it Rouven?
No, Rouven was correct. Actually, it's in German. It's Michels. I would have said Michels, but
Rouven Michels.
Rouven Michels. That's perfectly fine.
I'm going to try. Rouven Michels is a postdoctoral researcher in statistics at the University of Bielefeld in Dortmund in Germany. His research focuses on statistical modeling and machine learning, in particular on hidden Markov models, state-space models, and tree-based methods applied to sport data. He focuses on event and tracking data from various sports, such as soccer, American football, and handball. Let's welcome our speaker.
Yeah, thank you very much for the kind introduction. Probably all of you are hungry, so I will try to hurry up a little bit. Today I will talk about American football as well. And this is a joint project with Robert, who you have seen this morning, and Jan Ole, also from Bielefeld University. And this is an ongoing project, so comments are welcome at the end. So when I was invited to give this talk here, they said, okay, bring your own pictures. And it was like, oh shit, I wanted to show something pre-motion. And I asked my wife, did you have a picture when we were in Baltimore 3 years ago of pre-snap? And well, luckily she had, so I can show you something here. So the first defensive task is to decide between man and zone coverage. And as you can see here, Baltimore on the right side, the Bengals on the left side. The decision is here to take, okay, do we play man or zone coverage? And then the offense has to react. So they have to react to what they see or what they seem to see. Here, in this case, you see one, I think it's a tight end, standing upright. And I think with that, they motion this player and they try to decode the decision of whether to play man or zone coverage by using pre-snap motion. And, well, obviously, you can do this visually and see what's going on, especially for the defense and for the quarterbacks, how the defense reacts to that. But our aim is to set up a statistical model that forecasts the defensive scheme based on pre-snap motion. So this is the idea. And now I would like to briefly sketch the roadmap. So as you probably have seen, the name of the talk is The Best of Both Worlds, Supervised and Unsupervised Learning. So let's start with supervised learning. So what we are doing is we predict man and zone coverage based on features before motion with ML model. We do the same with also this naive post-motion features. Why do I say that there's this lavishly? Well, this is a classical classification problem. And this is why I just say ML models. You can use any tree-based model, or you can also use a logistic regression model. This won't be the focus of the talk here. What we focus on is the unsupervised learning, because we say, okay, we want to model the defender's pre-snap player movements with a hidden Markov model, where the underlying states correspond to the offense players to be guarded by the defenders. And from that, we would like to calculate summary statistics of the decoded state sequence and put them as additional features into our supervised model. So we have an outer loop, so to say, with the supervised model, and we have, so to say, an inner loop with the unsupervised learning here. And this is mainly the focus of this talk here, to tell you how this works, because a hidden Markov model probably, who knows about hidden Markov models? Not too many. So I have a kind of short introduction. But first of all, let's talk about the data. And thanks, Kwon, that you saved one minute for me by presenting the data of the last year's Big Data Bowl, where we have tracking data for the nine weeks. And what we did is we cleaned the data a little bit. In particular, we put out plays with bunch formations with two quarterbacks, and we focus on pass plays with pre-snap motion. And then we have like our final data set where we have like 74% in zone coverage and 26% in man coverage per PFF. They manually notated that. Yeah. And what do we fill in to the supervised learning before motion is like general play-by-play information, such as the down, yards to go, remaining seconds in the half. And also convex hulls spent by both teams. You can see this in this plot here. And the x-y coordinates of the 5 most relevant players per team. We will come to that in a second, what this is. And what data we use for the motions is much more bigger. So we have approximately 1.2 million x and y coordinates of the 5 most relevant players, whereas this, so the classification only lives on the play level, whereas the motion data and particularly the hidden Markov model lives on the tracking data, so time series model. That's why we use a time series model. Okay, probably you ask yourself, okay, what are the 5 most relevant players? So this is our leading example throughout my talk here. This is a play between Arizona and Kansas City. So in the end, Travis Kelce will score a touchdown. And what we see here is on the right side is Kansas City, left side is Arizona. And obviously, well, motion happens for skilled players. So what do we vanish? Here, of course, the quarterback and the offensive line. And well, then we end up with 5 skilled players. They are here like in 11 personnel, one running back, 1 tight end, 3 wide receivers. And we would like to match this for our model. So what do we put out for the defense is, of course, well, those players which do not move. This is the defensive line, so interior and defensive ends. We filter out the positions. But also we want to filter out those linebackers which are most likely to pass rush, so outside linebackers at the line of scrimmage, and also deep safeties. And if we filter also them out, you can directly see this 5-to-5 correspondence, which is our data ongoing now. Okay, with that, we would like to start, or I start now to present you the hidden Markov model, and I will start to present it in a very general way. So a hidden Markov model consists of 2 processes, one observed process here at the top, and one hidden process, and of course they are connected in a way, namely that each xt is generated by one of n state-dependent distributions. N is the number of states. And the state process, the underlying state process, selects which of the n distributions is active at any time, with the state here in time t is only depending on the state at time t-1. That's why it calls hidden Markov model. So maybe to understand that model in general, imagine, I also draw an example from biology. Imagine you have tagged an animal and you want to learn something about the behavior, and then you have tagged it and you see at the GPS things and you see, okay, he's like, the step lengths are short, 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 middle-sized, 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 long, long, long. Then with that model, you have probably 3 states. One state is like a sleeping state with only short step lengths, a foraging state, and a traveling state. And from that, you can deduce the behavior of an animal from the observed data. Okay? And the important part here is that the underlying Markov chain, which is estimated, because if we wouldn't have that, it would be just a classical mixture model. Here is another plot how you can view the hidden Markov model. On the left side, you see the Markov chain in time, and on the right side, and this is very important because we will see the connection to our specific case in a minute, are the state-dependent distributions. So I said the observations are generated by n state-dependent distributions. Here n is equal to 2, so we have 2 states, 2 distributions, one normal with a low mean, one normal with a higher mean. And here you can see the observations. So here are the numbers. And in general, this means that this data point stems from this distribution, this data point from this, and so on and so forth. And not only that, because only this would be a mixture model, but it follows also some persistence. So it's more likely that you stay in the state that, for example, I don't know, if I sleep 1 hour or the animal sleeps 1 hour, then it will probably sleep in the next hour as well. So we have also a time dependence between those values. So this is in general a hidden Markov model. And how do we transfer this now to our case? So in our case, guarding assignments between defenders and offenders cannot be observed, but inferred from the defender's responses to the offensive player's movements. So if the offensive player moves, probably something happens in the defense. And this is quite similar to a paper 10 years ago from Franks et al., who did this in basketball. So what are the processes in our case? The observed process is the y coordinate, so this coordinate, of the individual defender at time t. So we model the defender position. SD, the underlying process, is the offensive player guarded at time t. So again, we model the defender and we want to know who is the defender guarding. Similar to the biology. We model the step lengths and we want to know what is he doing. Okay? And the number of states equal to 5 because we say we have 5 skilled players. 1 of 5 offensive players can be guarded. And as with state-dependent distributions, we choose a Gaussian around the mean, where the mean is equal to the y-coordinate of the offensive player, which is quite reasonable, I think. The sigma is just being estimated. Okay? So this might be a little bit tricky, so I brought some more pictures for you. Let's investigate only Marco Wilson in this place. So we assume, which is a quite strong assumption, but for now we're doing this, that the defenders react or act individually. Okay, Marco Wilson is here, and here are the 5 possible offensive players who he could guard. Let's rotate this thing, because otherwise we cannot see like our y-coordinate that good. So here now is the interesting axis. So because here we say, okay, Marco Wilson is like mirroring, I think it's Nicole Hartman here. So let's put them on one line. And this is the only the only information we are interested in is where does this happen on this scale. And after we did this, I can show you this. And this now looks a little bit like what we've seen before. We have our player Marco Wilson, and he has to align to any of these state-dependent distributions. And of course, well, here it's most likely that he belongs to that one. And well, here you can see the connection to what we've seen before. In time point t equal to 1, this is our data point. And then the question is, okay, to what state-dependent distribution does this player belong? Well, obviously it's that one. And from this we can deduce, okay, to what player does this state-dependent distribution belong? Well, it's Nicole Hartman. Okay, this is similar to that case, but unfortunately it gets a little bit complicated because here on time, the 2 state-dependent distributions stay the same, right? Most often in hidden Markov models, the mean is estimated. Here, our mean is the position of the offensive player. So what's happening is that the offensive player like motions, and we can see that Marco Wilson is also motioning. And here the Markov property comes into play, because here, well, we have our data point and we have 2 slightly overlapping distributions where the model, or a mixture model, a classical mixture model, wouldn't be too sure, well, is it that state-dependent distribution which is active, or is it the other one? However, as we have our underlying Markov structure, we can say, oh, we have been in that state, so guarding that offender, in t-1, so we are very likely to guard him as well in the next period. And this is what happens here. And here, when we go even further, we can see that still Marco Wilson is trailing with Nicole Hartman, and thus also the state-dependent distribution is shifting from the right to the left. So this is the idea. And the idea then is to decode the states. Here, probably, and we will see that, Marco Wilson has a high probability to stay with the player, which could indicate man coverage. However, let's assume they are playing in zone coverage, then we would see more like shifts of the defenders, and we would see Marco Wilson maybe stick to this distribution. And with stick, I don't mean that we have to choose the distribution, but we get probabilities for that. So here in that case, we get very high probabilities for Michael Hartmann, but we also propagate uncertainty with the probabilities of the state-decoded sequence. Okay? So this is our general hidden Markov model framework, and now I will twist it a little bit. The first point is you can directly see here, we are trailing, we have a slight delay. So what do? We include lagged observations within the HMM, and because we expect defenders to trail these offenders, we allow for these lags, and we compare different models via AIC and see that a lag equal to 4 yields the best fit. So we go on from now with a lag of 4. And moreover, it's quite reasonable to assume that we have heterogeneity across positions and teams in terms of who is switching offensive players, and thus we include random effects for the position and also for the team into the transition probabilities. So from switching from offensive player 1 to offensive player 2, we include these random effects. And well, obviously you also have to estimate a global fixed effect. Okay, and now I'd like to briefly sketch the model fitting. So as already indicated, we assume independence between defenders, and thus we can multiply all time series likelihoods, and we numerically maximize this likelihood via the Llama package from my co-author Jon Ole and the RTMB package to speed up calculations. And for the decoding, there are also two possibilities, local and global decoding, and here again to propagate uncertainty and to assign for every defender and every time point a guarding probability of each offensive player, we do local decoding. Okay? So let's come to the results. You have done the hard stuff, so to say. First of all, let's come to the results of the HMM. So we have random effects, and we can look at the random effects, and we can see that here the Seattle Seahawks have the highest random effects, which means high means because we put it into the changing probabilities that they are more likely to change offensive players. So the defenders of the Seahawks are more likely to change the offenders. Okay? And the same we can do here for the positions, and we see that cornerbacks are more sticky to offensive players in contrast to linebackers, which pass on more the offensive players in comparison. And how do they fit into the transition probabilities? Well, for that, I brought you here is a resulting example of a transition probability matrix, which tells us, okay, for a specific combination of those two, I think I took Seattle and some position, we have a quite high probability to stick with my offensive players, and we have ordered them from the lowest to the highest from the initial y coordinate. And also we have some probability which is split up to the other offensive players. Okay? So this is quite nice because we see the persistence we would also expect. And this is now the decoded state sequence for the play we investigated the whole time. And you can see here, so this is a snapshot of the state probabilities of Marco Wilson in this play. So sorry, here's the QR code to the YouTube play, if anybody of you wants to see the touchdown of Kelsey. And here we can see that the probability that Marco Wilson is guarding the fifth player, so Michael Hartmann, is very high even throughout the sequence when he passes the running back. And this is the stark contrast to, for example, something like k-means clustering, where you forget about the time dependence. Because here the time dependence is very important because the model notices, okay, we're guarding him before that point in time and afterwards. So most likely you will also guard him if he's on the same y coordinate as the running back. Okay, so this is about this state sequence, and as I've indicated in the beginning, we would like to derive features from that because we want to put them into the outer loop, into our supervised learning. So what do? Well, we have a KV, we have decoded state probabilities as a multi-dimensional time series structure. And well, obviously we cannot just put them into a classification problem with only on the play level. So what do? We compute for each defender and time the most likely guarded offensive player and compute the sum of state switches and the number of defenders that switch players during a play. So these are the first two features. And similar to Franks et al., we also calculate the mean entropy across defenders by using the full decoded state probabilities, and with that we propagate uncertainty. And here higher entropy indicates greater unpredictability, which indicates less persistent guarding allocations, which could indicate to zone coverage. Okay, so let's put them into our model. And again, we fitted here GlimNet and an XGBoost, but they're exchangeable. So the focus is on what do we get from the motion. And what we get from the motion, if we look at accuracy, then we can see, okay, the XGBoost model is massively improved even by naive post-motion features. So we calculate a lot of naive post-motion features which could have captured all what happens in that play, but no, the H&M features go one step beyond and they provide even more information to our model, and we can see that not only for accuracy but also for the AOC and also for the negative log loss. However, these are just box plots, right? So, well, is there really differences? Well, yes, because we can use the things that Robert explained in the morning session, namely the statistical tests. And using these statistical tests, we can see that the number of player changes and the average entropy are both statistically significant addition to the naive post-motion features. And in general, those three are more or less exchangeable because they more or less measure the same, but altogether they provide information to the models before. And that's quite nice, and that's what we wanted to see. And as a, let's say, final analysis, we run some team analysis investigations and calculate the proportion of improved plays with the HMM features and without, so which can be like interpreted in, okay, who is really able to use pre-snap motion, so now from the offensive perspective. And well, we would say our model passed the Messi test from soccer, namely Kyle Shanahan and the San Francisco offense are on the top here in the teams which improved most by using motion. Okay, let's conclude. So what have we done? We modeled the pre-snap motion via HMMs, and that significantly improved the coverage prediction. And we included random effects, and they give insight into assignment of different positions and teams. And this is also really important because what I used here is a statistical modeling. This is in contrast to neural networks or just any AI thing. So you can interpret these models. Maybe they are a little bit worse in terms of prediction, but you can really interpret these things. And if you communicate with coaches, I could imagine that it could make more sense to use these models and have reliable estimates and uncertainties here. However, we are not at the end of the road. So the hidden Markov model framework is here to tell you, okay, what is possible with that, but it's even more possible. So what could we do? We could include the defender's X coordinates to use information of press, well, this off coverage. We could model the dependencies between different defenders via multivariate normal or copolars. And with more data, we could also use more complex models for the supervised learning. And the nice thing is that our HMM is modular, so you can fit this to the tracking data and you can derive the features and put this into the auto loop. So it's very modular, so very easy to apply for your model, so to say. And another outlook which could be interesting is to employ mixtures of HMMs to decode a scheme that includes both man and zone coverage. Similar done in football and soccer, sorry, in Germany it's football. In soccer, yeah. And these are my references, and if you have questions, comments, or want to go to the Patriots tomorrow with me, then tell me no or send me a message to my email address. Thank you.
We've got a few minutes for questions, and then we're going to lunch.
Thanks.
Thanks. Hey, great talk. So 2 questions. Can you go back to the slide with like the team rankings? Mm-hmm. Like the previous one with the, I think the Seahawks were on top. Yeah. So this is like the most like unpredictable, like highest like variability like offenses based on the different coverages, right?
So that means this comes into the transition probability matrix. Mm-hmm. So that means that they are most unlikely to switch between offensive players, which is an indication for zone coverage.
Oh, so that's just like the amount of plays that they play zone, or you would predict them to play zone?
It's the random effect, which is assigned to the Seahawks. And well, I cannot say that they play zone because it comes from the guarding assignments and the transitions between the players. But well, it indicates into that direction.
Right. Okay. Gotcha. Yeah.
Anyone else?
Hi, great presentation. I just had one question. Brian Flores, who's like the DC for the Vikings, he uses a lot of motion of his defenders that are not in response to motion from the offense. So I wondered how your model kind of like dealt with that.
Well, really good point. If there is no motion of the offenders, it probably won't be in our final data set because we don't see motion. Yeah, but it's a really good point. We should think about that. That's a good point. I mean, our perspective comes from the offense. The offense motions something and we react. But what you say is that they are the ones which are active, right? So this is kind of another problem, but an important one.
All right, well then let's thank our speakers again. Thank Ben and Kwang, Rouven.
Well done.